Hello my dear students, welcome back to Rapid Focus series of grade 12. I am Aswin, your chemistry faculty, here to explain some questions from the chapter coordination compounds. So moving on to the first question. What is the first question? Find coordination number and oxidation state of central metal atom or ion in the following complex. So that you can see a coordination complex or coordination compound is given and you have to find the coordination number and oxidation state. For that, what do you need to do? First of all, what is the given coordination compound? Cobalt, En twice, okay, Cl2, okay, and also one plus charge is there. So this is the coordination compound given in the question. And you have to find the coordination number. How can we find the coordination number? Can you tell me how can we find the coordination number? Coordination number is the number of ligand donor atoms. Number of ligand donor atoms. Okay, most of the students, they are misunderstanding that coordination number is the number of ligands. No, not at all. Okay, coordination number is not equal to number of ligands. It is equal to number of donor atoms. It is equal to number of donor atoms of ligands. That's why I define it like this. Coordination number is equal to number of ligand donor atoms. How many donor atoms are there in a coordination compound? That is the coordination number. So here in this question you can see what are the ligands here? Cobalt is a central atom. Okay, fine. What are the ligands present here? There are two ligands. One is En. You know what is En, right? What is En? Ethylene diamine, or you can also call it as ethane 1,2 diamine. Okay, so this is ethane 1,2 diamine. Ethane 1,2 diamine. And ethane 1,2 diamine is a bidentate ligand. It's a bidentate ligand. What do you mean by bidentate ligand? Bidentate ligands means these are ligands having two donor atoms. So there will be two donor atoms. Two donor atoms will be there. Okay. So you know that En is containing, that is one En is containing two donor atoms. One En is containing two donor atoms. How many En is there? Two Ens are there, right? So two En will be containing 2 into 2. So total 4 donor atoms. Okay, that's it. So you can see in our coordination compound, the first ligand is En, ethane 1,2 diamine. But this En is bidentate. Bidentate means one ligand will be having two donor atoms. So here you can see one En will be having two donor atoms. So how many En is there? Two Ens are there. So two En will be having 4 donor atoms. You got it? Yes. Then what's next? What is the next ligand? Chlorine is the next ligand. And chlorine is a monodentate ligand. You can see this is a chloride ion. It's a chloride. Anyway, this chlorine or chloride will be having, or it is a monodentate. It is a monodentate ligand. And since it is monodentate, one chlorine will be having 1 donor atoms. One chlorine will be having 1 donor atom. Okay, how many chlorine is here? 2 chlorines are there, right? 2 chlorines are there. So 2 chlorine will be having total 2 donor atoms. Okay, you got it? So these are the total number of donor atoms. What are the total number of donor atoms? From the ligand En, we got 4 donor atoms. From the ligand chlorine, we got 2 donor atoms. So total, can you tell me the total donor atoms? What are the total donor atoms? It is equal to 4 plus 2. You can see 4 donor atoms from the En ligand and 2 donor atoms from the 2 chlorine ligands. So total 6 donor atoms are there. 6 donor atoms are there. So we can confirm that coordination number is equal to 6. So we found the coordination number. So if coordination number is 6, you can see two options are there. Option C and option D. Okay, we can eliminate option A and B, because for A and B coordination number is 4, but C and D is having coordination number 6. So you have to find oxidation number also, then only you can find which is the correct answer. So how can we find the oxidation number of this particular compound? For finding oxidation number, what you need to do, this is the compound COEN twice Cl2, then a plus charge is there, right? And what is the next step you need to do? You can do take the oxidation state of cobalt as X. Take the oxidation state of cobalt as X. And oxidation, what is the charge of En? En or ethane 1,2 diamine ligand, it's a neutral ligand, it's a neutral molecule. So it will be, since it is neutral, the charge will be 0. Charge will be 0. So charge of En is 0. What about the charge of chlorine? Charge of chlorine is -1. Charge of chlorine is -1. So when we are adding all the oxidation state or all the charges together, you should get +1 charge. So what is the charge of cobalt? That is X, plus what is the charge of En? 1 En is having 0 charge. How many En is there? 2 En. So 0 into 2. It will be 0. Anyway, 0 into 2. Then 1 chlorine is having -1 charge. How many chlorine is there? 2 chlorine is there. So -1 into 2. And it should be equal to +1 charge. It should be equal to +1 charge, because +1 is there. Okay, above the compound you can see +1 charge is there. So can you do it? X 0 into 2, it will be 0. -1 into 2, it will be -2. So x minus 2 is equal to +1. So x is equal to +1 plus 2. You can take the -2 into right side, so it will become +2. It will become +2. -2 taking right side, it will become +2. So 1 plus 2, it will become +3. So the oxidation state of central metal cobalt in this compound is +3. So coordination number is 6 and oxidation number is +3. So which is the correct option? Option D is the correct. That's it, simple. So this is a question that you can expect from the terminologies or from the basic things of the coordination compound chapter. From the introduction part, you can expect this question, finding the oxidation state and coordination number. Second question is IUPAC name of the complex CONH3 5 times NO2 Cl2. That is, a compound is given and you have to find the IUPAC nomenclature. Easy. So what is the compound given? Cobalt NH3 5 times. Okay. Then NO2 is there. NO2 is there. Okay. Then what is remaining? Chlorine is there. That's it. So how can we name this? How can we name this compound? Whenever a coordination compound is given in the question, what you need to do is, you have to remember this point. A coordination compound always will be in this form, either in this form, that is a coordination sphere and a counterion, or it will be in this form, a counterion and coordination compound, or it can be two coordination coordination spheres. This can be two coordination spheres together. Oh, okay. Anyway, then you have to consider this as the first part. You can call it as first part. And this will be the second part. You can call it as second part. Okay. And here in this coordination compound, which will be the first part? Yes, your counterion will be the first part. And this can be called as second part. Okay, and whatever here, this will be the first part and this will be the second part. This will be the second part. Okay, so always remember, a coordination compound can be these types. That is, first a coordination sphere, then a counterion, or first counterion, then coordination sphere, or two coordination spheres can be there. In this case, always, first part will be always positive part. You can call it as positive part or cationic part. Second part is negative part. You can call it as negative part or anionic part. Similarly, in all these cases, first part will be always positive part. Second part will be always negative part. Okay, so in this question, here is this is the first part, and this will be the second part. And what is the first rule you need to remember? What is the first rule you need to remember when you are doing IUPAC nomenclature of a coordination compound? You know, whenever you are doing IUPAC nomenclature of a coordination compound, you have to start with the first part or positive part. So you have to start with the first part. Okay, but you can see your first part is a coordination sphere. So whenever you are doing IUPAC nomenclature of a coordination sphere, you have to start with the names of ligands. You have to start with the names of ligands, because in a sphere there will be central metal and ligands. Here cobalt is the central metal, NH3 and NO2 are the ligands. So you have to start with the names of the ligands. But another problem is there. What is the problem? Here more than one ligand is there. If more than one ligand is there, what you will do? You have to follow alphabetical order. So what is the name of NH3? Name of NH3 is amine. And what is the name of NO2? What is the name of NO2? You know, if NO2 group is came, okay, as a ligand, you know, you remember this thing. NO2 can be either given in the form of NO2 or it can be given in the form of ONO. What is the difference between this? Both are actually NO2, nitro groups. Okay, in IUPAC nomenclature of coordination compound, we call it as nitrito. But what is the difference between them then? Can you tell me? You know, if in the question, if it is given like NO2, then the meaning is, you know, nitrogen is the donor atom. Then the meaning is, in this ligand, nitrogen is the donor atom. What do you mean by donor atoms? Do you know what is donor atom? Donor atom is the atom of a ligand which can directly bond with the central metal. Understood? And in the question, if it is given like ONO, then oxygen will be the donor atom. That means oxygen will be making direct bond with the central metal. So this is the point you should remember. If in the question, if it is given like NO2, then nitrogen will be the donor atom. Then you have to name it like nitrito N. Okay. And if it is given like ONO, then you can name it like nitrito O. Okay, nitrito N and nitrito O. This is the way of naming it. And can I ask you a question? You know, these kind of ligands are known as? Yes, correct. Ambidentate ligands. What are ambidentate ligands? Ambidentate ligands are ligands that will be having more than one donor atoms. Okay, same ligand, but they can make direct bond with the central metal through nitrogen and also through oxygen. So these kind of ligands are known as ambidentate ligands. That's an additional point. Okay, it can be a question, one more question. What is ambidentate ligand? Or it can be an objective question. Giving the example, they can ask an objective question. Okay, so study it. Now you got it, right? What is ambidentate ligand? Ambidentate ligands are ligands which can make, or two donor atoms will be there. Not at a time. At a time only one donor atom will be there, but two different donor atoms are there. In this case, nitrogen is the donor atom, but in this case, oxygen is the donor atom, but ligand is same. That kind of ligands are known as ambidentate ligands. Anyway, here you can see it's NO2, not ONO, it's NO2. So if NO2 came, what will be the name? It is nitrito N. Okay, nitrito N. Now we can start naming. Now we can start the nomenclature of this coordination compound. I'm starting with the first part. This is the first part and this is the second part. Okay, so I'm starting with the first part. In this first part, I'm starting with the ligands. What are the ligands here? Amino group, amine group and nitrito N group. And according to alphabetical order, amine group will you should write it first. amino group. How many NH3 are there? How many NH3 is there? 5 NH3 is there. Okay, so how can we name? You know, if 2 NH3 is there, you can name it like diamine. If 3 is there, triamine. If 4, tetraamine. If 5, you can say pendaamine. Correct. You know, pendaamine. Correct. Pendaamine. Okay, so we named the amine group, the NH3 group. And what is the next ligand? NO2. What is the name of NO2? Nitrito N. Only one NO2 is there. So you can directly write a nitrito, then N. Nitrito N. So we wrote the names of both the ligands. And what is remaining in your first part? Your first part is coordination sphere. We wrote the names of ligand. What is remaining? Central metal. What is the central metal here? Cobalt. So you can write cobalt. That's it. Finish. Okay. So the nomenclature is finished. But you have to write oxidation number of central metal. Central metal is cobalt. What is the oxidation number of cobalt here? You have to find it. Find it. How can we find it? You know, cobalt is X and NH3 the charge is 0. NO2 charge is -1 and chlorine charge is -1. How can we find it? I'll tell you how can we find it. You know, when you are finding oxidation state of a central atom, you can always start from the counter ion. If counter ion is there, you can start from the counter ion. That will help you. That will make you, easy to find this, oxidation state. So here there is a counter ion. So I'll start with counter ion first because it will be easy then. I'll tell you, counter ion. What is counter ion? Chlorine. You can see chlorine is having -1 charge. How many chlorine is there? 2 chlorine. So total charge will be -2. Total charge will be -2. So the second part or the negative part, this thing, negative part is having -2. Total -2. So what will be the total charge of positive part? It should be +2. Understood? Chlorine, counter ion, 1 chlorine is having -1. How many chlorine is there? 2 chlorine is there. So -1 into 2. So total charge of the negative part is -2. So total charge of the positive part should be +2. Then only it will be cancelled. Okay, so we got the charge of the positive part. What is the charge of the positive part? The positive part is cobalt, NH3 5 times, NO2, then this is the positive part and it is having a +2 charge. This is having a +2 charge. Now you can easily find it. What is the oxidation state of cobalt? X. What is the oxidation state of NH3? 0. What is the oxidation state of NO2? It is -1. Understood? Yes. Now you can easily find it, X plus 0 because this is 0. The charge of NH3 is 0. How many NH3 is there? 5 NH3 is there. So 0 into 5. Okay. Plus what is the charge of NO2? -1. How many NO2 is there? Only one NO2 is there. Okay. So it should be equal to +2. So x minus 1 is equal to +2. So x is equal to -1. If you are taking right side, it will be +1. So total it will be +3. So oxidation state of cobalt is +3. We got it +3. Okay. So I'm putting the 3 in Roman numeral. So we wrote the name of the first part. Then what is remaining? After naming first part, you can name second part. What is the second part here? Second part is chloride. How many chlorine is there? 2 chlorine. So you will write dichloride. That is mistake. That is a common mistake. Students are making this common mistake. Since they are seeing that 2 chlorine, they will write dichloride as the name of the second part. But don't do that. It can be 2, it can be 3 chlorine, it can be 4 chlorine. Don't write, the di, tri, tetra prefixes. Okay, don't write it. Just write what is there? Chloride. So you can write chloride. Enough. You don't need to write dichloride, trichloride. Okay, whenever you are writing the IUPAC nomenclature for the counter ion, you don't need to write the di, tri, tetra. Just write the name of that counter ion. Yeah, the counter ion is chloride, so I wrote pendaamine nitrito N cobalt 3 chloride. Where is it? Pendaamine it's O, so this is wrong answer. Second one, pendaamine nitrito N cobalt 3 chloride. Yes, this is the correct answer. Option B is the correct answer. We got it. That's it. So that's the second question. Yes, I'm moving on to the third question. What is the third question? The correct name of platinum NH3 4 times, copper CN 4 times. Oh, again it's a UPSC nomenclature question. How can we do this? How can we do this? Again, yeah, I'm starting with the compound platinum NH3 4 times, NH3 4 times. Okay, and you can see what is there, CuCN 4 times, right? Yes. Now I told you in the last question, a coordination compound can be these types. And what type is this? Our third question is in this form. In this form, 2 coordination spheres are there. So the first coordination sphere is the first part, second coordination sphere will be the second part. So here you can see this is the first part, this is the first part, and this will be the second part, this will be the second part, and this will be the first part. Okay, then what is the rule? What is the rule? Whenever you are writing the UPSC nomenclature for coordination compound, start with the first part. This is the first part. And first part is a coordination sphere. When you are writing the name of a coordination sphere, you have to start with the name of ligand, then only the name of central atom. So what is the ligand here? What is the ligand here? Can you tell me what is the ligand? It's amine. How many amine is there? 4 amine. So how can we write it? Tetraamine. Yes, we did it already in the last question. If NH3 group is came as a ligand, we can name it as amine. 4 NH3, so tetraamine. And yeah, I wrote the name of the ligand. So I'm moving on to the central metal. How many central metal is, what is the central metal here? Platinum. So you can write platinum. Okay, tetraamine platinum. Tetraamine, okay, ligand, name of the ligand, and platinum, name of the central atom. But you have to write the oxidation number of central atom in bracket. So what is the oxidation number? Can you tell me what is the oxidation number? How can we find it? Again, here there is a problem. What is the problem here? Here there is no counter ion. I told you in the last question, if there is counter ion, you can first find the charge of counter ion, then the opposite will be the charge of the other part. Okay, but here there is no counter ion at all. Then how can we find the charge? Do you have any idea? Yes. Here you can see for both the coordination sphere, for both the central atom, their coordination number is same. For platinum, coordination number is 4. For copper, coordination number is 4. Then their oxidation number will be also same. That is, platinum will be having an oxidation state of X. Suppose I am taking it as X. And copper will be also having a coordination number of X. Okay, because we need to find both. So I am putting both as X. Okay, and also what is the charge of NH3? What is the charge of NH3? It is 0. What is the charge of cyano group? Cn. What is Cn? It's called cyano group, right? We call it as cyano. Yeah, of course, your cyanide or nitrile group we studied in in the organic chemistry. Yes, and here we call it as cyano. Anyway, what is the charge of the Cn group? It is -1. It is -1. It is -1. So how can we name this? How can we name this? We can name this like this. Before naming, we need to find the oxidation state, right? How can we find the oxidation state? Platinum, okay, NH3 4 times, and copper Cn 4 times. Here it is X 0, X -1. So here it will be X plus 0. Okay, plus here there is X plus here minus 1. For 1 Cn it is minus 1. How many Cn is there? 4 Cn is there. So minus 1 into 4. So we added all the charges and it should be equal to 0. It should be equal to 0. When we are adding all the charges, it should be equal to 0. Then x plus x. What is x plus x? 2x. 2x minus 1 into 4. Minus 4 equal to 0. So x is equal to, 2x is equal to, you can take the minus 4 into right side. So it will be plus 4. So x will be equal to plus 4 divided by 2. It is equal to plus 2. It will be equal to plus 2. It will be equal to plus 2. Okay, so the oxidation state of platinum is plus 2. That means x is plus 2. So oxidation state of platinum is plus 2 and also oxidation state of copper is plus 2. Now you can write the name. Tetraamine platinum 2. Tetraamine platinum 2. I wrote the oxidation state of platinum. Then I finished the first part. Then you can move on to the second part. In second part, again it's a coordination sphere. So you have to start naming with the name of ligands. And the ligand here is cyano group. How many cyano group is there? 4 cyano group is there. So you can name it like tetracyano. Okay, tetracyano. So I wrote the name of the ligand. Then I can write the name of central metal. What is the central metal there? In the second part, what is the central metal? Copper. So what you will write? You will write it like copper. And again the same mistake you are repeating again. Don't write it like copper. Why? Most of the students, they will make this mistake, common mistake. Students are making this as a common mistake. Why? Remember the next point, the next rule you need to remember while doing IUPAC nomenclature for coordination compound. What is that? When you are writing the name of a coordination compound, if the sphere is in the second part, or if the second part is a sphere, if the second part is a coordination sphere, then along with the name of the central metal, you have to add ATE, 8. Do you remember? If iron came, we will call it as ferrate. If silver came, we will call it as argentate. If cobalt came, cobaltate. Chromium came, chromate. Right? Similarly, here it's copper. So along with the copper, you have to add 8. But don't write it like copperate. Okay, because copper, here you need to write the Latin name. What is the Latin name of copper? It's cuprum. So you can see, you can add 8 with that. So you will get cuprate. You will get cuprate. You will get cuprate. So remember that point whenever you are doing IUPAC nomenclature of coordination compounds. If the second part is a coordination part or a coordination sphere, then along with the name of the central metal you have to add 8. Okay, and most of the for some metals we will write the Latin name. Okay, so here it is copper, so Latin name is cuprum, but since it is in the second part, you have to add 8 with it, so that we got cuprate. And what is the oxidation state of cuprate? It's 2. So yeah, I putting 2. Tetraamine platinum 2 tetracyano cuprate 2. Tetraamine platinum 2 tetracyano cuprate 2. That's it. Option A itself is the correct answer. Finish. Now the fourth question. This can be a question because many pre-board exams they ask this question. 1 mole of complex COCl3.6NH3 on reaction with AgNO3 gives 3 moles of AgCl precipitate. The secondary valency of complex is. Maybe instead of the secondary valency, they will ask the common question. What is the common question? Write the structural formula of the complex. Instead of asking secondary valency, they can ask write the structural formula of the complex. Okay, both steps will be same for all. Okay, anyway, let's see. In this question, what is given? You can see in this question 1 mole of a complex COCl3.6NH3 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 on reaction with AgNO3 giving 3 moles of AgCl. You are getting 3 moles of AgCl. You are getting 3 moles of AgCl. You are getting 3 moles of AgCl. Okay, so this is what is given in the question as a precipitate, and the secondary valency you have to find. It's a question from the first theory of coordination compound. What is the first theory? Werner's theory. In Werner's theory, you are studying 2 types of valencies or 2 types of linkages. What are they? Primary linkage and secondary linkage, or primary valency or secondary valency. So here they ask the secondary valency. So how can we find the secondary valency, or what is secondary valency? Secondary valency is nothing but coordination number. Secondary valency is a non-ionizable valency or linkage, which is nothing but our coordination number. And what is coordination number? We studied. What is coordination number? How can we find coordination number? It is the number of donor atoms. It is the number of donor atoms. So let's find the coordination number. But if you want to find the coordination number, you have to write the structural formula of the complex compound given in the question. But only this thing is given in the question. From this you have to find the structural formula. But there is a hint, because our compound, when react with AgNO3, they are making 3 moles of AgCl. 3 moles of AgCl. If you want to make 3 moles of AgCl, 3 chlorine should be there outside the sphere. Cobalt as a central atom, okay, and there should be 3 chlorine outside. There should be 3 chlorine outside the sphere as counter ion. Then only we will get 3 AgCl. 1 AgCl is having 1 chlorine, so 3 AgCl means 3 chlorines are there. So if you want to get 3 AgCl, 3 chlorine should be there outside the sphere. Okay, so yeah, this will be the thing. And what is the remaining? 6 NH3, that you can put it like this. NH3 6 times. Now we got it. Now we got the structural formula of the compound. Now we got the structural formula of this complex compound. Understood? So if it is in the question, let's consider like 2 AgCl. If it is 2 AgCl, how many chlorine will be there? Tell me, how many chlorine will be there? 2 chlorine will be there outside. 1 chlorine will be there inside as a ligand. Understood? If it is 1 AgCl, only 1 chlorine will be there outside the sphere, and remaining 2 will be inside the sphere as a ligand. That's it, simple. Okay, so now you got the structural formula of the compound. I told you maybe the question will be structural formula. If they are asking structural formula, yes, our answer is finished. Okay, but here they asked secondary valency. What is secondary valency? It's coordination number. What is the coordination number of this compound? Can you tell me what is the coordination number of this compound? Easy. Coordination number is the number of ligand donor atoms. What are the ligands here? NH3. NH3 is a monodentate ligand. NH3 is a monodentate ligand. Monodentate ligand. You should study examples of monodentate ligand, bidentate ligands. Okay, and also the polydentate ligand. One of the important example for polydentate is EDTA. You know that EDTA. It is hexadentate. It is hexadentate. That can be a question. Hexadentate. Hexadentate means 6 donor atoms will be there. 6 donor atom. Another example. Okay, anyway, extra point. But here NH3 is a monodentate. Monodentate means only 1 donor atoms. Only 1 donor atoms. Okay, only 1 donor atom. So 6 NH3 is there. So total 6 donor atom. 6 donor atom. So therefore coordination number will be 6. If coordination number is 6, then you can say your secondary valency will be also 6. So answer is D. Option D is the correct answer. Hope you understood this. Easy? Yes. So we covered Werner's theory using this question, and we covered IUPAC nomenclature of coordination compound using the last two questions. And the first question is from the terminologies, the introduction part of coordination compounds, finding the oxidation state and the coordination number. That's it, finish. Okay, now we are moving on to the next topic, that is isomerism. So this fifth question is from the isomerism topic. So what is the question? The compound CrH2O 6 times Cl3 and CrH2O 4 times Cl2 Cl2 dot H2O represent linkage isomerism. Option B, hydrate isomerism. Option C, ligand isomerism. And option D, none of this. Option D, none of this. What do you think? What will be the correct one? Let's see. For that, I am writing, the compounds given in the question. What is that? CrH2O 6 times, then Cl3. Then Cl3. That is the first compound given. What is the second compound given? CrH2O 4 times Cl2. Okay, and a Cl2 is there outside. A Cl2 is there outside. Sorry, a Cl is there outside, and also 2H2O is there. 2H2O is there. Okay, this is actually 2H2O. Okay, I wrote it correct here. Okay. So these are the two compounds given in the question. First one, CrH2O 6 times Cl3. Second thing, CrH2O 4 times Cl2 Cl dot 2H2O. So we need to find which type of isomerism is there in between these two compounds. How can we find it? We studied many types of, especially from structural isomerism, we studied 4 types of isomerism, right? And we need to find what type of isomerism is this. From this itself, you can easily identify it is hydrate isomerism or solvate isomerism. Option B will be the answer. But for understanding the concept, I will tell you how to find it. If you don't know, I will tell you how to find it. How can we find it? First of all, you have to confirm that this is an isomer. How can we confirm that these two are isomers? Same number of atoms will be there. 1 chromium, 6H2O, 4 plus 2, 6H2O is there in the right side also. 3 chlorine, 2 plus 1, 3 chlorine. So confirm it is an isomer because they are having same molecular formula. But what is the difference between them? What do you think? What do you think? What is the difference between them? This is not having any H2O here outside, but this is having H2O outside, right? As dot H2O. If it is dot H2O, you can call a compound as hydrated compound. Okay, so this is not a hydrated compound, this is a it's a hydrated compound. But the point is, molecules having same molecular formula but difference in the number of H2O molecules as ligands. Okay, so same molecular formula, okay, same molecular formula but different number of H2O molecules as ligands. Then you can call it as hydrate or solvate. This hydrate isomerism is also called solvate isomerism. Okay, so this can be written like this. The same thing can be written like this. Cr is there, okay, and H2O. How many H2O took here? 4, right? So I can write it like 5. And 1 chlorine can take inside. So how many chlorine is remaining? 2 chlorine is remaining. And how many H2O I took outside? 1 H2O. This can be another. It can be another isomer of this. Because here also you can see, number of Cr, number of H2O, number of chlorine. Everything is same. So it's an isomer, but the difference is the number of H2O molecule as a ligand is is changing. Okay, and it is the difference in H2O molecule is coming as a hydrate. Then it is confirmed that it is a hydrate isomerism, or it's also called solvate isomerism. That's it. So we finish the structural isomerism part. But the next isomerism is geometrical isomerism, because we can classify the isomerism as structural isomerism and stereoisomerism. Structural isomerism, I told you four isomerisms you should study. Linkage isomerism is there, ionization isomerism is there, okay, solvate isomerism is there, coordination isomerism is there. Study it with example. Okay, so that structural isomerism part is finished. What is with the stereoisomerism part? Stereoisomerism can be further classified into two. What are they? Geometrical isomerism and optical isomerism. Okay, so definitely the next question will be from geometrical isomerism. So here you can see, out of the following, which complex will show geometrical isomerism? Easy question, because I have a trick for you. What is the trick? If you want to find whether a complex or whether a coordination compound will show geometrical isomerism or not, I have a trick. What is that trick? If you want to find geometrical isomerism, you can split this into two. What is that? First one is a square planar, geometrical isomerism for square planar complexes. And the second thing is for octahedral complexes. Okay, for square planar compounds, you can take this one. I mean, for square planar complexes, if it is having a formula or the coordination compound is in the form ML2X2, or if the coordination compound is in the form ML2XY, or the coordination compound is in the form MABXY. If your coordination compound given in the question is in these three forms, then the coordination compound will show geometrical isomerism. It will show geometrical isomerism. You can say that it will be showing geometrical isomerism. M is a central atom. Okay, these are some general formulas for types of coordination compounds. And you can see here, M is representing the central atom, L is representing the first ligand or any one ligand, X is representing another ligand, Okay, so a central atom with two different ligands, then it is in the form ML2X2, then they will be having geometrical isomerism. They will be showing geometrical isomerism. Or if your coordination compound is in the form ML2XY, M is the central atom, L is one ligand, and X is another ligand, Y is another ligand. So total three ligands are there. Three different ligands are there. Total number of ligands is 4. 2 L ligands, 1 X and 1 Y. So total 4 ligands are there. And if the coordination compound is in this form, then you can say that they will be showing geometrical isomerism. Another example is MABXY. What do you mean by that? What do you mean by this? M is the central atom, A is one ligand, B is another ligand, X is another ligand, Y is another ligand. That means 4 different ligands are there in this coordination compound. If 4 ligands are different, then they also showing geometrical isomerism. That's it. Easy. Okay. And if you want to find octahedral complexes, what you will do? For octahedral complexes, these are the general formulas to remember. That is, for octahedral complexes, M, L Ml4x2, Ml4x2, Ml4x2. Second one Ml4xy, Ml4xy. Okay, and third one Mll2, Ll2x2, Ll2x2, and fourth one Mll2xy. Yes, these are the general formula for the coordination compounds which are showing geometrical isomerism. So these are for octahedral complexes and these are for square planar complexes. How can we identify this is octahedral or square planar? It's easy, because if the coordination number is 4, they will be square planar. If the coordination number is 6, then it will be octahedral. So you can ask, sir, in this case coordination number is 4, so how can it be octahedral? No guys, it's not coordination, it's not 4. For this compound, coordination number is not 4, it's again 6. Why? Because this LL is representing bidentate ligand. So one LL will be having 2 donor atoms. So 2 LL will be having 4 donor atoms, and again 2 more, so total 6. Okay, so central atom, 4 ligand, 2 another ligand. If your complex is in this form, then they will be showing geometrical isomerism. Central metal and 4 ligands, X and Y, another 2 different ligands, then they will be also showing geometrical isomerism. Central metal, 2 bidentate ligands, LL means bidentate, LL2 means 2 bidentate ligands, and 2 another ligands, they will be also showing geometrical isomerism. Central metal, 2 bidentate ligands, one ligand, another ligand, so total 3 different ligands with 2 bidentate, then they are also showing geometrical isomerism. Okay, so using this you can easily predict whether a compound will show geometrical isomerism or not. Okay, so let's see, this question, platinum NH3 twice Cl2. You can see in this case, this question, this compound, platinum, okay, NH3 twice and Cl2. Can you tell me what type of, what is the coordination number here? What is the coordination number here? Can you tell me? NH3 is a monodentate. How many NH3 is there? 2. So 2 donor atoms. Cl, chlorine is also monodentate. How many chlorine is there? 2 chlorine. So 2 donor atoms. So total 4 donor atoms. If it is 4 donor atoms, then it will be square planar complex. For square planar complex, these are the general formula for the compounds having geometrical isomerism. So you can see, we can check whether this compound is in this form or not. We can see a central metal is there, M. Platinum is the central metal, M is there. Then a ligand, NH3 is a ligand. How many NH3 is there? 2 NH3 is there. And chlorine is another ligand, X. How many chlorine is there? 2. So you can see now this compound is in the form Ml2x2. Ml2x2 can show geometrical isomerism. So we finish. We got the answer A. Option A. It can show geometrical isomerism. That's it, simple. So you, in this way you can check it whether it is square planar or octahedral. Check just this. You need to check only this, whether the given compound is in this form or not. If it is in this form, then you can say they will show geometrical isomerism. That's it. Hope you understood this. Okay. So can we move on to the next question? Are you okay? Yes. Now the 7th question, draw the geometrical isomers of complex. A complex is given and you have to draw the geometrical isomers. Guys, how can we draw geometrical isomers? What do you think? In the last question we studied how can we find whether a compound will show geometrical isomerism or not, right? With respect to the formula, general formula, you can predict it. whether a compound will show geometrical isomerism or not. But here you have to draw the geometrical isomerism. Now we should study some theories. I mean some concept related to geometrical isomerism. What is geometrical isomerism, guys? Geometrical isomerism is nothing but it is an isomerism in which same molecular formula, compounds will be having same molecular formula but different spatial arrangements or different arrangement of ligands. Arrangement will be different. Okay, same molecular formula but arrangement of ligands will be different. That is what is geometrical isomerism. Okay, I will show you some examples. With this example, I can show you this example. Platinum En twice Cl2. The first task is for you. What is that? You have to tell me whether this compound will show geometrical isomerism or not. It will show because already in the question it is there. Okay, you have to draw the geometrical isomerism. That means it is showing geometrical isomerism. But how can we find it? How can we find this? Because the question is platinum En twice Cl2 and 2 plus. And let's check the formula. Platinum, the central metal. En, what do you mean by En? It is ethane 1,2 diamine. Ethane 1,2 diamine or ethylene diamine is a bidentate ligand. So you can represent it like LL. How many bidentate ligands are there? 2. Okay. And chlorine is another ligand. I am representing it like X. How many chlorine is there? 2. So X2. That's it. So now you can see MLL2X2. Can you check here? MLL2X2. Yes, MLL2X2. This compound can show geometrical isomerism. So in this way you can say that this compound can show geometrical isomerism. Now we should draw that. How can we draw that? Geometrical isomerisms can be of two types: cis isomerism and trans isomerism. Cis isomerism means same ligands will be in the same side. Trans isomerism means same ligands will be in the opposite side. So let's start with this compound, platinum. Okay, I'm writing the central metal, platinum. Okay, platinum. And I told you, from this it is clear, coordination number is 6, so it will be an octahedral complex. Octahedral, what is the shape of an octahedral complex? This is the shape of an octahedral complex. Okay, and one En is there. En, we know that En is a bidentate ligand. So En, it will be having 2 donor atoms. Okay, how many En is there? 2 En is there. So one more En I am writing. Yes, one more En. You can see En is having 2 donor atom. One donor atom, another donor atom. One donor atom, another donor atom. Okay, and what is remaining? So platinum, 2 En and 2 more chlorine is there. So one chlorine here, another chlorine here. Finish. And not only that, there is a 2 plus charge. Since there is charge, you have to mention the charge like this, 2 plus. In this way you can write. Okay, this is the way of drawing one of the geometrical isomerism. And what is this? What type of geometrical isomer is this? You can see similar ligands are similar in same side. En is in same side. Chlorine is in same side. So same ligands on same side. Then you can call it as cis isomer. Okay, so this is cis isomer. Can we draw the trans isomer? What will be the trans? Trans means same ligands will be in opposite. So platinum again, octahedral manner, and one En. Okay, and another En will be just opposite side. Here will be the next En. Understood? And the remaining chlorine will be here. And 2 plus charge. Yes, 2 plus charge. Finish. You know guys, you know this is in here you can see same ligands in same opposite side. En and opposite side, they are opposite side. So same ligands in opposite side, same ligands in opposite side. So you can call it as trans isomer. You can call it as trans isomer. That's it, finish. Hope you understood this. Easy, right? You know, now we studied how can we predict whether a compound is showing geometrical isomerism or not, and also we studied that how to draw the geometrical isomers, cis isomer and trans isomer, right? That's it, easy. This can be a question, okay? Yes, next question. For the complex FeH2O 6 times 3 plus, write the hybridization, magnetic character and spin of the complex. Of course, after isomerism, we are studying VBT, valence bond theory, or bonding in coordination compounds. And from VBT or valence bond theory, you should study this thing. I mean, it will be a direct question at all. That means, you can easily score from this topic, because since it is a direct question. They will always ask a coordination compound will be given, and they will ask hybridization, and they can ask structure, or they can ask magnetic character or magnetic property, or they can ask the spin, I mean low spin, high spin concept. Okay, that also we will discuss here in this question. So I'm starting with the FeH2O 6 times. FeH2O 6 times. FeH2O 6 times, and also a 3 plus charge is there. 3 plus charge. Okay. So when a given compound, a coordination compound is given, what do you need to do? First of all, you have to find the oxidation number of central metal. Okay, whenever a question is asked for finding hybridization, or finding the magnetic property, or finding the spin, you have to, first step is you have to find the oxidation state of the central atom. Central atom is iron. How can we find oxidation state? I'm putting it as X, and this H2O. What is the charge of H2O, guys? H2O is a neutral molecule, so charge will be 0. Now, can you add it? X plus 0 into 6. That means 1 H2O, it's 0. How many H2O is there? 6 H2O. 0 into 6 should be equal to, what is the charge? Plus 3. So X is equal to plus 3. That's it. So we got the oxidation state of iron. What is the oxidation state of iron? It is plus 3. So listen, iron, it is having atomic number 26. So electronic configuration will be argon 4s2 3d6. Argon 4s2 3d6. That is the electronic configuration for iron. But here we studied that iron is having oxidation state plus 3. Plus 3 oxidation state means, 3 plus means 3 electrons are donated or losing of 3 electrons. So 3 electrons will be loose from which point? From 4s we can remove 2 electron, and from 3d from 4s we will remove 2 electron, and from 3d we will remove 1 electron. So 4s will be 0 here, and 3d 6 was there, 1 electron is removed, so total 5. That means for Fe3 plus the electronic configuration will be argon 3d5. Argon 3d5. Hope you understood this. Initially iron is having electronic configuration argon 3d5 4s2, and Fe3 plus means 3 electrons are removed, 2 electrons from 4s and 1 electron from 3d6. So 4s, there will be no electrons after removing 3 electrons, and from 3d we remove 1 electron, so it will be 3d5. Now you can see how many electrons are there in the 3d? 5. So the next step is you have to draw an orbital diagram of 3d. Yes, I am drawing an orbital diagram of 3d. 1, 2, 3, 4, 5. Yes, 3D. This is an orbital diagram for 3D. And you know how many electrons are there in this 3D? 5. So 1, 2, 3, 4, 5. 5 electrons are there in the 3D orbital. Okay, 5 electrons are there in the 3D orbital. And you can see after this 3D there will be 4s and also 4p. There will be 4s and 4p. This is 4s orbital and this is 4p orbital. And what is the next step? So do you always remember the steps? Okay, first step, find the oxidation state. Second step, using the oxidation state, write the electronic configuration. Third step, orbital diagram. I wrote the orbital diagram. Okay, and what is the next step? Please check the ligand. If the ligand is a strong ligand, pairing will take place. If the ligand is a weak ligand, pairing will not take place. What do you think? H2O is a strong ligand or a weak ligand? H2O is a weak ligand. So pairing will not take place. So you can say like this. That is, since H2O is a weak ligand. H2O is a weak ligand. H2O is a weak ligand. Pairing will not take place. Pairing will not take place. Pairing will not take place. So what will happen? If pairing is not happening, you know, the 3D will be here. I mean, the electrons in the 3D will remain there. Electrons in the 3D will remain there. 1, 2, 3, 4, 5. And also, what is the problem? You know, since there is 6 ligands are there. 6 ligands are there. We need 6 vacant orbitals. 6 ligands. So we need 6 vacant. So from 4s we will get 1 vacant. From 4p we will get another. You know, 3 orbitals. Now it is only 4. 1, 2, 3, 4. 4 vacant orbital. So the remaining 2 can be take from the next 4D. This is 4D. So from 4D you can take the 2 vacant orbitals. So I am taking 2 vacant orbitals from 4D also. So you know what happened here is, you know, according to, I told you, this question is from VBT, valence bond theory. According to valence bond theory, how a ligand and central metal is making bond between them. You know, central metal will provide vacant orbitals, and these like this. Okay, how many ligand is there? That much vacant orbitals will be provided by central metal, and these vacant orbitals will undergo hybridization. Okay, and after hybridization they will form hybrid orbitals, and to this hybrid orbitals ligands will attach. So that is the concept. So here you can see, according to the nature of the ligand, since it is weak ligand, you know, pairing will not take place. This pairing of electron will not take place. So 3D is already filled completely. I mean, you can see 5 unpaired electrons are there, but we need vacant orbitals. How many ligands are there? 6 ligands. So we need 6 vacant orbitals. So that's why I took 1 orbital from 4s, 3 orbitals from 4p, and 2 orbitals from 4d. And when this one s is there and 3p is there and 2d orbitals are there, and when these orbitals undergoing hybridization, they will form sp3. sp3 how many d is there? 2. So sp3d2. This will become sp3d2. All the 6 orbitals will become sp3d2. This will be also sp3d2. This will be also become sp3d2, and this will be sp3d2. Similarly, all of them will become sp3d2. And after this hybridization, the ligands will be attached. I mean, the ligands H2O will be attached to this. H2O will be attached to this. That's it. 6 ligands, 6 H2Os are attached to the hybridized orbitals. So this is the way of forming the complex Fe H2O 6 times 3 plus. Okay, and from this it is we can easily find the hybridization. What is the hybridization? How can we find the hybridization? Hybridization, what is the hybridization? What are the orbitals we used here? S orbital, 3 p orbitals and 2 d orbitals. So hybridization is sp3d2. So hybridization we got. What is the hybridization? sp3d2 is the hybridization. sp3d2 is the hybridization. Okay, so you can note it separately. Okay, when you are writing this in exam, please note it separately. Hybridization they asked, and the hybridization we got it. It is sp3d2. And the next one, magnetic character. Magnetic character mainly depends on the presence of unpaired electron. If there is unpaired electron, you can see even in your last complex, it is having unpaired electrons in the 3d orbital. So presence of unpaired electron makes them paramagnetic. Presence of unpaired electrons makes them paramagnetic. So you can say magnetic property is paramagnetic. They are paramagnetic. Why they are paramagnetic? It is simply due to the presence of unpaired electrons makes them paramagnetic. If all electrons are paired, okay, if all electrons are paired like this, then it should be diamagnetic. Okay, but here it is unpaired, so presence of any unpaired electron makes them paramagnetic. And the last one is spin. How can we predict the spin? Actually, what is spin? What do you mean by spin? They are asking, like, is that a low spin or a high spin complex? Low spin complex means low spin is also called as low spin, high spin, and also called as low spin is also called as inner d orbital complex. High spin is also called as outer d orbital complex. Okay, outer d orbital. So what do you mean by that? How can we find whether a compound is low spin or high spin? There is a trick, I will tell you. Here you can see in this case what type of d orbital we used, or which d orbital we used here. It's not 3d, we used 4d. If you are using 4d means the outer one, 3d means the inner d orbital, 4d means outer d orbital. So if you are using outer d orbital, you can call it as outer orbital complex or high spin complex. Okay, if you are using this 3d orbital for hybridization, then you can call it as low spin complex or inner d orbital complex. So here we used the outer d. Outer d means 4d. If you are using the 3d, you can call it as inner d. Okay, so here we used outer d orbital. Here we used outer d orbital. So you can call it as it is high spin. It is high spin complex. Okay, if it is inner d orbital, you can call it as low spin complex. Okay, low spin is also called spin paired, and high spin is called spin free complex. That also question can be asked. Okay, so that's it. Now we found hybridization, magnetic property, and spin. Okay, whenever they are asking hybridization, please do follow these steps. First, you have to find the oxidation state. From the oxidation state, you can write the electronic configuration. From the electronic configuration, you can draw the orbital diagram. And after drawing orbital diagram, check the nature of the ligand. If it is strong ligand, pairing will take place. And if it is weak ligand, pairing will not take place. Okay, if pairing is not there, then you have to, if pairing is there or not, you have to take the vacant orbitals, which is in number it is same as the number of ligand. Yeah, I took it there. vacant orbital, and they will undergo hybridization. You will get the corresponding hybridization, and also from that, with respect to the presence of paired and unpaired electron, you can predict the magnetic property, and also the spin also you can predict. With respect to spin can be predicted with respect to what d orbital you used. Okay, that's it. And next question, explain as to how the two complexes of nickel but nickel tetracarbonyl have different structures but do not differ in their magnetic behavior. That means nickel is, the given compounds are nickel Cn 4 times, nickel Cn 4 times 2 minus. Okay, and the second one is nickel CO, nickel CO 4 times, nickel tetracarbonyl. Okay, so these are the two different coordination compounds of nickel, and they said that they are having different structures. They are having different structures, but do not differ in their magnetic behavior. Why? Give reason question. It can be a give reason question. They are having they are having different structures but do not differ their magnetic property. How can we find this? Yes, the same steps you need to follow. The same steps. Can you do it? Same steps you need to follow. For nickel, what do you need to do? First, you have to find the oxidation state. So for first oxidation state, nickel, oxidation state X. This is -1. So it will be like, X. X plus -1 into 4, it will be equal to -2. Okay, so x minus 4 equal to -2. So x is equal to -2 plus 4. So x is equal to plus 2. You got it? This is the oxidation state of nickel in this compound. What is the oxidation state of nickel in this compound? Before that we can find the hybridization if you want. How can we find the hybridization? It's simple. How can we find it? Using after finding oxidation number, what is the next step? Write the electronic configuration. Nickel electronic configuration is argon. What is the atomic number? Atomic number is 28. You have to study it. Okay, study the atomic number of nickel, cobalt, everything you need to study. So nickel 28, argon, so 4s2, 3d8 it will be, and nickel 2 plus, because oxidation state is +2. So I want to write the electronic configuration for nickel 2 plus. For nickel 2 plus, you need to remove 2 electrons. From where you will remove 2 electrons? From 3d or 4s? Yes, of course, from 4s you need to remove 2 electron, because even though the last electron is filled in 3d, you have to remove electrons from 4s. So argon 3d8. Now you got the 3d electrons. What is the next step? Yes, orbital diagram. You have to draw the orbital diagram. How can we draw the orbital diagram of 3d? 3d 1 2 3 4 5. So how many electrons are there? 8 electrons. 1 2 3 4 5 6 7 8. These are the 8 electrons in the 3d orbital, and few more orbitals are remaining there. 4s will be there, and also 4p will be there. This is 4s and 4p. After 3d, 4s will be there, and also 4p will be there. What is next step? After drawing orbital diagram, what was the next step? With respect to the ligand, you need to do pairing or pairing or not. So here Cn. What is Cn? Cn is a strong field ligand. It's a strong ligand. So since it is a strong ligand, what will happen? Pairing will take place. So since it's a strong ligand, pairing will take place. So pairing will take place. Since you can write, since Cn is a strong ligand, Cn is a strong ligand, pairing will take place. So pairing, this will turns into here. That means after this you can see, after this 3D will be filled like this. 1, 2, 3, 4, 5, 6, 7, 8. Pairing is finished. And one 3D will be vacant. One 3D will be vacant here. One 3D orbital is vacant. Okay. One 3D orbital is vacant. One 3D orbital is vacant. Okay. And you know how many ligands are there? 4 ligands are there. 4 ligands are there. So we need four vacant orbitals. So one we will take from 3D and one we can take from 4s. Okay, and so 2 is there. 2 more we need. So 2 orbital you can take from 4p. 2 orbital you can take from 4p. 4p also, from 4p also I took 2 orbital. So one from D, another from S, and 2 orbitals are from P. Now they will undergo hybridization. These vacant orbitals will undergo hybridization. So they will form dsp2 hybridization. What is the hybridization here? ds, how many p is there? 2p. So dsp2. dsp2. How many orbitals are there? dsp2 orbitals. Hybridization is happened there. So we got the hybridization dsp2. dsp2. Similarly, you can find the hybridization of nickel tetracarbonyl. Can you find it? I'm giving it that. I'm giving that to you. Nickel tetracarbonyl. You have to find the hybridization of nickel tetracarbonyl like this. Find it. Okay, and if you are finding, you will get the hybridization as sp3. You will get the hybridization as sp3. Similar way, in the similar way you can find it, because the carbonyl group is also a strong ligand. So pairing will take place and you will get sp3 hybridization. And we know that with respect to the hybridization, you can predict the structure. How can we predict it? If the hybridization is dsp2, then the structure will be square planar. Then the structure will be square planar. Square planar. If the hybridization is sp3, then the structure will be tetrahedral. Tetrahedral. Then the structure will be tetrahedral. Understood? And if the hybridization is sp3d2, sp3d2 or d2sp3, it will be octahedral. Octahedral. Okay, so these are the points you need to remember, but here we need only these 2 points. A dsp2 structure is square planar. That means this compound is having square planar structure. Nickel nickel Cn 4 times 2 minus. This is having a square planar structure. It is having a square planar structure because it is having a dsp2 hybridization. So it is having square planar structure. And nickel tetracarbonyl, it is having sp3 hybridization. So it will be having tetrahedral arrangement. That's why in the question they said, now we got why they are having different structure. Okay, why they are having different structure. And they said that they do not differ in their magnetic behavior. They do not differ in their magnetic behavior. Let's see. You can see, I told you, both Cn and Co, both are the strong ligands. Both are strong ligands. So here pairing is take place, and also you can see no unpaired electron. Every electrons are paired electrons. So presence of paired electrons makes them diamagnetic. Okay, diamagnetic. And what about nickel tetracarbonyl? I told you CO is also strong ligand. So there will be also pairing. In 3D orbital there will be also pairing. So every electrons will get paired. Okay, every electron will get paired. So that you can say that they will be also paired. They will be also having paired electrons, so that you can say presence of unpaired electron makes them diamagnetic. Okay, so that's the point. They are different in structure. one is having square planar, another is having tetrahedral, but they do not differ in their magnetic behavior. Why they do not differ in magnetic behavior? It's simply because of the first compound is having a strong field ligand, so undergoing pairing, and since there is pairing, there is no unpaired electron. In nickel tetracarbonyl also there is no unpaired electron. There will be pairing. You can do it. You can, in the same manner we did already two, right? So that you can do it. Okay, so try it. You can see after pairing, everything will be paired electrons. There will be no unpaired electrons. So that's why this is also diamagnetic. That's it. So that is the question. Hope you got the reason behind it. Both of them are having paired electrons. There is no unpaired electrons. So they will be diamagnetic in nature. Okay, and the 10th question, FeH2O 6 times 3 plus is strongly paramagnetic, whereas FeCN 6 times 3 minus is weakly paramagnetic. Strongly paramagnetic, weakly paramagnetic. How can we predict the paramagnetic nature like this? Strongly, weakly. We are predicting like, whether it is a paramagnetic or diamagnetic. How can we predict is it a strong or weak paramagnetic? Yes, there is a trick. I will tell you. I'm starting with FeH2O 6 times 3 plus. We remember we did this already. We did this question already in the previous case. You can see in the previous question we did this. Yes, FeH2O 6 times 3 plus. And here you can see this is the way you need to do. You need to find the oxidation state, and after finding oxidation state you need to draw write the electronic configuration. After electronic configuration you can draw the orbital diagram. Then with respect to the nature of the ligand is H2O is weak ligand, so pairing will not take place. So 3D will be having 5 unpaired electrons. So how many unpaired electron is there in this compound? How many unpaired electron is there? 5 unpaired electron is there. So you can do it here also. You can apply that here also. In this question also the same compound is there, and you can say that this compound will be having how many unpaired electron? 1, 2, 3, 4, 5. So number of unpaired electrons is equal to 5. Number of unpaired electron is equal to 5. You got it? Number of unpaired electron is equal to 5 in this compound. What about the next compound? FeCN 6 times 3 minus. FeCN 6 times 3 minus. In this case, what is the next? How can we find the number of unpaired electron? Yes, do the same thing. You do the same thing. You have to do it. Okay, but here we can do if you want. First of all, you have to find oxidation state, ion X and the cyanide minus 1. So X plus minus 1 into 6 should be equal to minus 3. So X minus 6 is equal to minus 3. So X is equal to minus 3 plus 6. So it equal to plus 3. So how can we draw Fe3 plus, Fe, what is the electronic configuration of Fe? Fe is equal to, argon 4s2 3d6. And Fe3 plus means argon 2 electron will be removed. 2 electron will be removed from 4s and 1 electron will be removed from 3d. So it will be 3d5. Okay, and D is having how many electrons? 5 electrons. 3d is having 5 electrons. 1, 2, 3, 4, 5. 5 electrons are there. But the problem is, here you can see the ligand is a strong ligand, CN. Cyano group, it is a strong ligand. So since CN is a strong ligand, what will happen? Pairing will take place. So it will get paired. This will come to here and this will come to here. So what will happen? It will get paired like this. 1, 2, 3, 4, 5. So you can see how many unpaired electron is there? Number of unpaired electron here. Number of unpaired electrons is equal to 1. Here number of unpaired electron is equal to 5. Since there is unpaired electron, you can say that both are paramagnetic in nature. Both are paramagnetic in nature. Why? Because the presence of unpaired electron. Both are paramagnetic. But here the question is, which is strongly paramagnetic and which is weakly paramagnetic. You can see, more the number of unpaired electron, more the paramagnetic property. So here this compound is having more number of unpaired electron. So this compound will be more or strongly paramagnetic. So this is having, since it is having more number of unpaired electron, this will be strongly paramagnetic. This will be strongly paramagnetic. This will be strongly paramagnetic. Understood? And this compound is having only one unpaired electron. So this will be weakly paramagnetic. This will be weakly paramagnetic. Weakly paramagnetic. This will be weakly paramagnetic. This will be weakly paramagnetic. Understood? Okay. So that is, that's the thing. So remember that point. What is the relation? More the number of unpaired electron, more will be the paramagnetic nature. That's it. Okay. Next, move on to the next question. On the basis of crystal field theory. Yes, we are in the last theory. Now we are in the last theory. 3 theories we are studying in this chapter. That is Werner's theory, VBT, valence bond theory, and the last one, CFT, crystal field theory. So this is a question from crystal field theory. On the basis of crystal field theory, write the electronic configuration of D4 in terms of T2G and EG in an octahedral field when delta O is greater than P and delta O is less than P. What is crystal field theory? You know what is crystal field theory, right? Crystal field theory, according to crystal field theory, when a ligand is approaching the degenerate d orbitals, they will split into T2G and EG orbital. Okay, I'm not explaining that much because we don't have enough time. We are mainly focusing on the questions, right? You should get the question. If you want, please tell me. We can do another video. Okay. Yes. So the point is, on the basis of crystal field theory, write the electronic configuration of D4. You have to write the electronic configuration of D4. That means a d orbital having 4 electrons. And the point is, in terms of T2G and EG, in an octahedral field, it's an octahedral complex, and delta O, what is the first condition? Delta O is greater than P. Okay, what do you mean by delta O? Delta O is nothing but it is crystal field splitting energy, okay, of octahedral complex. That delta is indicating crystal field splitting energy. You know that splitting, right? Initially a ligand will be, this is the degenerate orbital. This is the degenerate orbital. Initially this will be the degenerate orbital. Okay. But what will happen? When a ligand is approaching, initially it will turns into an average energy. Okay, it will turns into an average energy. Then after that they will split. When the ligand is approaching, they will split into T2G and EG. T2G and EG. T2G and EG. They will split like this. So this is energy. You can see this is what is happening in CFT, crystal field theory. This is what is happening. Initially a d orbitals are there. You can call it as degenerate orbital. When ligand is approaching, they are having an average energy and they will split. Okay, and when they are splitting, one orbital, this set of orbital will be having energy less than this degenerate orbital, and another set will be having higher energy. So that is what is T2G and EG. And there will be an energy gap between the T2G and EG. That is what is delta O. The energy gap between EG and T2G is known as delta O. And what is P? Now you got the delta O, right? Yes. What is P? P is the pairing energy. And if delta O is greater, okay, greater the gap, that means the ligand, the approached ligand is a strong ligand. Okay, if the splitting is more, that means the delta O is more, then the approached ligand or the ligand present in that complex is a strong ligand. If the splitting is low, I mean it is very small splitting, then you can say that the approached ligand or the ligand in the complex is a weak ligand. So here you can see splitting is more, that is delta O is greater than P. That means splitting energy is greater than pairing energy. That means the approached ligand, splitting is more. So the approached ligand will be a strong ligand. Approached ligand will be a strong ligand. Okay, then you should remember, if it is a strong ligand, what will happen? What will be the pairing? T2G will be here, T2G will be here, T2G, and EG will be here, EG will be here. There will be a large gap between T2G and EG. There will be a large gap between T2G and EG. So how 4 electrons will be filled in this D? You have to fill 4 electrons in this D. How it will be filled? This is delta O. So since it is strong ligand, I mean the delta O is very high, high. You can see 4 electron can be filled like this. T2G 1, 2, then 3. The 4th electron will not go to the EG. Why? Because EG, you can see the distance is very high. I mean the energy gap is very high. Okay, so the 4th electron will not go to the EG. It will be paired like this in T2G. Understood? So remember this concept. This is the point. If delta O is greater than P, that is indicating it's a strong ligand. If it is a strong ligand, splitting will be very high. Since the splitting is high, the 4th electron will not go to the EG. It will be paired in the T2G itself. Understood? That's why we said in the VBT, what is that? If it is a strong ligand, pairing will take place. Understood? In VBT, when we are finding hybridization and the magnetic property, we studied what is that? If it is a strong ligand, pairing will take place. Now you understood why, right? Because strong ligand, more will be the splitting energy. More the splitting energy, the 4th electron will not go to the EG. It will be paired in the T2G. So what will be the electronic configuration of D4? In this case, in the first case, the electronic configuration is this. T2G, how many electrons are there in T2G? T2G 4. And EG, how many electrons are there in EG? 0. So this is the electronic configuration. This is the electronic configuration for the first case. And the second case, you can do it by yourself. Can you do it? Delta O is less than P. That means delta O, I mean the splitting energy or the energy gap, that is very, very low. I mean very small. Energy gap is very small. If the energy gap is very small, this means energy gap is very small. Delta O is less than pairing energy. That means this is very small. P is pairing energy. If you don't know, please note it. Okay, pairing energy. Pairing energy. Okay, delta O. What is delta O? It is the energy gap. It is the energy gap. Okay. Anyway, if the energy gap is less than pairing energy, you can say that it is a weak ligand. It is a weak ligand. So since it's a weak ligand, the distance between T2G, the distance between T2G and EG, the distance between T2G and EG, this is T2G, T2G, and this is EG. The distance between T2G and EG will be very small. The distance between T2G and EG is very small. You can see this is the distance. This is the distance. Only very small distance. You can see here since it was a weak ligand, the splitting energy or the energy gap will be it was very large energy gap. But here it is very small energy gap. Why? Because it was a weak ligand. Since it is a weak ligand, energy gap is very small. So how can we fill 4 electrons in this d orbital? How can we fill 4 electrons? 1, 2, okay, 1, then 2, 3, and the 4th electron will go to the EG. Why? Because the energy gap is very small. So the 4th electron can enter into the EG. but here energy gap was very high, so fourth electron will not go to the Eg, it will be paired in the T2G. But here, since the gap is very small, the fourth electron will enter to the Eg. So what will be the electronic configuration here? T2G, how many electrons are there? 3 electrons. Eg, how many electrons are there? 1 electron. That's it. Okay, so we got the electronic configuration of D4, electronic configuration of D4 in terms of this and in terms of this. The point you should remember is this: if this is given as a question, as a condition, remember it is a strong ligand. It is a strong ligand. If delta O is greater, if it is strong ligand, it will be a strong ligand, and this is a weak ligand. It is representing a weak ligand. Strong ligand, distance will be high. The energy gap will be large. Okay, then pairing will take place. If it is a weak ligand, energy gap is very small, so pairing will not take place initially. It will go to the Eg. That's it. Finish. Hope you understood this, right? Yes. So that's it. So that is what is some questions from the coordination compounds chapter. Hope this video help you in your board exams. Okay, we'll be seeing few days. After a few days, we will meet again with another chapter, D and F block elements. And until then, thank you. Bye.